Tutorial 5, Flight Controls. This flight training tutorial will discuss flight controls. To control an aircraft, a pilot must manipulate the aircraft's control surfaces to maintain a desired trajectory or assigned vector. Learning how control surfaces affect the attitude of the aircraft is important for safe and efficient flight. Flight controls are what allow the pilot to control the forces of flight and the aircraft's direction and attitude. Different flight control systems exist for different types of aircraft. The most basic control systems are mechanical and date back to early aircraft. They are used today on sport and small general aviation aircraft in which the aerodynamic forces are not excessive. They operate by mechanical connections between the control stick and the control surface. In this case, the control stick is attached by pulleys to the elevator. As flight control systems become more complex, mechanical circuits were developed to reduce the weight and limitations of mechanical systems. The control stick is used to move control valves on the mechanical circuit which controls cylinders which move the control surfaces. As technology progressed even further, modern aircraft are controlled by electric motors, digital computers, or fiber optic cables called fly-by-wire systems. This flight control system replaces the physical connection between pilot controls and the flight control surfaces with an electrical interface. There are two types of flight control systems: primary systems and secondary systems. Primary systems consist of ailerons, elevator, and rudder. Secondary systems consist of wing flaps, spoilers, and trim systems. The primary control system changes the pressure of the airflow around the airfoil. These changes in the airflow allow a pilot to move the aircraft around its three axes of rotation. The ailerons control roll about the longitudinal axis. The ailerons are located on the outboard trailing edge of the wings. They work opposite to one another. If the pilot moves the control stick to the right, the aileron on the right side of the plane will move up, and the aileron on the left will move down. This combined motion causes the plane to roll to the right. Adverse yaw is caused when a plane rolls to the left or right. In a roll to the left, as illustrated by the picture, the right aileron moves down to provide more lift and roll the airplane to the left. During this process, the aileron also produces more drag. As a result, the plane yaws toward the raised wing or to the outside of the bank as seen by the pilot. The pilot must apply rudder pressure to account for the adverse yaw. This effect is magnified at slower speeds because of the decreased effectiveness of the vertical stabilizer and rudder. There are four major systems that are used to counteract adverse yaw. The first system is coupling the ailerons with the rudder pictured on the left. When the rudder moves in conjunction with the ailerons to correct for aileron drag. The second system is differential ailerons pictured on the right. The aileron that deflects downward does not move as much as the aileron that deflects up. This helps by increasing drag on the descending wing, thus eliminating most of the yawing effect. The third system is called the freeze-type ailerons, pictured on the left. These ailerons move on an offset pivot, which causes them to be pushed into the airstream when deflected upward, which causes drag. These ailerons also have slots, which allow for smoother airflow over the lowered aileron, making it more effective at high angles of attack. The fourth and last system is called flaperons, pictured on the right. Flaperons combine the aspects of the ailerons and the flaps. The pilot can move the flaperons like conventional ailerons, or the pilot can lower both simultaneously, like flaps. The elevator controls pitch about the lateral axis of the airplane. The elevator, which is located on the trailing edge of the horizontal stabilizer, is controlled by pushing the control stick either forward, which causes the elevator to move down and the nose to pitch down, or back, which causes the elevator to move up and the nose to pitch up. Pitching the aircraft happens about the plane's center of gravity, labeled CG on the right. The elevator on this plane is the T-tail type. This means the elevator is positioned high on the vertical stabilizer so as to remove the horizontal stabilizer from exhaust blast and prop wash. Because it is removed from prop wash and therefore not receiving constant airflow, the pilot of a T-tail aircraft must make large control movement when flying slowly to control the nose. A stabilator works in much the same way as an elevator, but instead of a trailing edge control surface, the entire horizontal stabilizer moves up and down along a pivot point as shown above. A stabilator downspring may be used to increase nose down pressure if the center of gravity was placed aft. Also, an anti-servo tab is placed on the back of the stabilator to decrease the effect of moving the control surface. This decreases pilot-induced overcontrolling. The canard design places a horizontal stabilizer in the front of the plane before the main wings. The canard actually produces lift to keep the nose up, which is theoretically more efficient than using the horizontal stabilizer surface to lift the nose up, which results in less drag for a given amount of lift. The rudder controls the aircraft movement around the vertical axis. This movement is called yaw. The rudder is connected to the vertical stabilizer and is controlled by the rudder pedals in the aircraft. If the left pedal is depressed, then the nose of the aircraft will yaw to the left. The Beechcraft Bonanza shown above has a V-tail design. This design incorporates rudder vators, which are a combination of the rudder and the elevator, and they work much like flaperons. The pilot is able to control the rudder and elevator separately, but the control surface acts as both. Secondary flight controls may consist of wing flaps, leading-edge devices, spoilers, and trim systems. Flaps are the most common high-lift devices on an aircraft. They are attached to the trailing edge of the wing and increase both lift and drag for any angle of attack. There are 4 main types of flap: plain, split, slotted, and Fowler flaps. The plain flap is the most simple of the flap designs. This design increases the camber of the wing, which causes greater lift, but also greatly increases drag. The split flaps deploy from the lower surface of the wing and increase lift slightly more than the plain flap. Both the plain and split flap designs cause high drag for little lift. The slotted flap is the most popular flap used today. The slotted flap allows high-energy air to flow from the bottom of the wing to the top of the wing. This movement of the air causes a much greater lift force than either the plain or split flap. The Fowler flaps work much like slotted flaps, but they not only change the wing camber, they also increase the wing's surface area. They slide back and down rather than just down. High-lift devices may also be added to the leading edge of the wing. The 4 most common types are fixed slot, movable slot, leading edge flap, and leading edge cuff. Fixed slots delay airflow separation until a higher angle of attack. This does not increase the wing's camber, but still increases lift. The movable slot works in the same way as fixed slots, but either open when the angle of attack is increased or by the pilot at any angle of attack. Leading edge flaps work to increase the camber of the wing and are commonly used with trailing edge flaps to reduce the nose-down pitching tendency. Leading edge cuffs work to increase the wing's camber and lift. The front edge of the wing is pushed down and forward, allowing for more air to connect with the upper surface of the wing at higher angles of attack, thus reducing the aircraft's stall speed. Spoilers help by reducing lift and increasing drag over the wing surface. Spoilers are used in gliders to control descent, and also in large aircraft to control adverse yaw, because when they are deployed, they increase drag on the lower wing, which stops the plane from yawing to the outside of the bank. Also, deploying both spoilers at the same time increases drag and are used to slow down and reduce ground roll by transferring weight to the wheels and thus increasing braking efficiency. Trim systems are used to relieve the pilot of the need to maintain constant pressure on the flight controls, and usually consist of controls in the airplane and small hinged devices attached to the trailing edge of one or more of the primary flight control surfaces, such as the elevator, rudder, and ailerons. In small aircraft, they are usually manually controlled by a small vertically mounted control wheel. In small aircraft, the wheel moves the trim tab on the elevator, causing the plane's nose to pitch up or down. The pilot usually establishes a desired power setting, pitch attitude, and configuration, and then trims the controls to relieve the pressure required on the controls. Shown above is a balance tab. This tab automatically moves opposite the control input to automatically relieve some of the pressure required to be held by the pilot. The linkage of the flight controls and the tab is controllable from the flight deck. Anti-servo tabs, pictured on the left, work in much the same way as balance tabs, by opposing the force of the pilot and making the stabilizer less sensitive. Ground adjustable tabs, as seen on the right, can be adjusted from the ground and stop the aircraft from skidding left or right during cruising flight. Rather than using a movable tab on the trailing edge of the elevator, some aircraft have an adjustable stabilizer. This setup connects the stabilizer to a jack screw and is controlled by either a trim wheel or crank on a smaller aircraft and a motor on larger aircraft. Autopilot is an automatic flight control system that keeps an aircraft in level flight or on a set course. It can be directed by the pilot, or it may be coupled to a radio navigation signal. The autopilot reduces the physical and mental workload of a pilot by controlling the aircraft about 1, 2, or 3 of its axes during flight. A simple autopilot, as shown above, might be able to only keep the nose of the aircraft in level, pitch up or pitch down flight. Another autopilot system might only be able to keep the wings level or be able to turn to a certain heading. More complex autopilot systems can control the aircraft about all 3 axes, and even more advanced autopilots will have a feature that allows for specific vertical speeds or airspeeds. The autopilot system works with inertial navigation systems, global positioning systems, GPS, and flight computers to control the aircraft. To maintain safety, the autopilot incorporates a disconnect feature to disengage the system automatically or manually. We hope you learned a lot. Please help us spread the word about Pilot Training System, and we look forward to further servicing your flight training needs.